Let me start by a small introduction about zeta functions, just as a reminder. And so the basic setup will be that I take now FQ to be the finite field with Q a power of P elements where P is a prime. Secondly, take X to be an algebraic set of dimension D defined over FQ. So for example, X can be given by M polynomials with coefficients in FQ as a vanishing set of those polynomials. And with this, and finally, define NK to be the size of the set of solutions on X with coefficients in FQ to the K. So this is extensions of FQ, and then you're considering the size of the set of solutions on the algebraic set. Okay. And if you're really concerned about extending this beyond varieties, you can take a schema finite type and then tensor with the the closure of FQ, and you get something that makes sense. So with these things in mind, so this is just the number of solutions of on X in FQ to the K, we can define a generating function called the zeta function of X, and it's given as zeta a power series in T. In particular, the exponential of the sum from K equals 1 to infinity of NK divided by K times T to the K. And this, as I said, lives in, obviously it has coefficients in Q, and it's a power series in the variable T. Okay. And so with this, I come to the first theorem of today. It's a very well-known theorem. It's the Weyl conjectures theorem, and a part of it. And it says that if X is a smooth projective variety of dimension D, excuse me, defined over FQ, then, well, let me continue over there. So the zeta function of X is a rational function it's a rational function of the following form. So in the numerator, you have a product of polynomials, P1 of t, P3 of t, and so on until P2d minus 1 of t, where d is the dimension of the variety. And the denominator, you have P0t, P2t, so all the even ones, P to the 2d t, where we know a little something about the form of these polynomials, and that's that P0 of t is just 1 minus t, P2d of t, so the first guy here and the last guy here in the denominator, takes the form 1 minus q to the dt. Okay. And for all other I, so for I greater than or equal to 1 and less than or equal to 2d minus 1, we have that the corresponding polynomial pi of t factors into a product over some index j. It's not important what j goes to for purposes of this talk, of 1 minus alpha ij t. where alpha ij, so alpha ij are algebraic integers, and the absolute value of alpha ij equals q to the I over 2. And now this is the absolute, the regular, just your usual absolute value, because after all, this is just a function with coefficients in q. Stuff like that makes sense. Okay, so this was proven a while back, when not too far back, when Ariko was a grad student, and they're very useful. You'll see. So let me start with an example. So I'll let x be the projective line, okay, over fq. So what does that mean? Well, first of all, these numbers nk just equal q to the k, the number of elements in fq to the k, plus 1 for the point at infinity, okay? And so what does that mean for the zeta function? Well, the zeta function of projective line is then, by definition, the exponential of the sum of q to the k plus 1 divided by k. And this is k goes from 1 to infinity, t to the k. And so I can rewrite this as the exponential of the sum, k goes from 1 to infinity, of qt to the k divided by k times the exponential of the sum over k from 1 to infinity, t to the k over k. Okay? And so this equals the exponential of minus log 1 minus qt. And this one equals the exponential of minus log 1 minus t. And what does that mean for the zeta function? It means that the zeta function of the projective line is just 1 divided by 1 minus qt times 1 minus t. Okay. So it's about as simple as you can get as far as zeta functions go, because you have to, well, for smooth varieties, you have to have this term and this term, and so everything else is just 1. Okay. And so another example, which I won't really work out, but let x be an elliptic curve, for example, hyperelliptic curve, a curve of some kind. Then what you know is that zeta of this variety has to take the form p1 of t divided by 1 minus qt, 1 minus t. And this is immediate from the theorem. And this guy factorizes into some product of factors according to that formula over there. Neat. And so as you might expect, the roots of, and in fact, these alpha ij's detect a lot of information about the number of points on the corresponding variety. Okay, but let's switch gears for a second and talk about mirror symmetry. Okay, so here's an example. So first, consider a family of quintic 5 Calabi-Yau hypersurfaces. Okay? And now to construct a mirror family, let x lambda consist of the one parameter family of guys defined by f of x0 to x4. And I'm going to put a little subscript lambda here. So the sum of xi to the fifth, I goes from 0 to 4, plus lambda, the product from I goes from 0 to 4 of xi. So this is just the quintic threefold family from yesterday. So it's a one-parameter family. And this isn't the mirror yet. So you take all quintics on the one hand, and on the other hand, you consider this one-parameter family. And then I claim now that there's a group action of z over 5z to the cubed, which acts by scaling on the variables xi, okay? That leaves that polynomial invariant. And in fact, I said that this is a family of x lambda defined by this equation. So it's not just, it makes no sense to call it a polynomial. Anyway, so now, okay, so you have this your quintics, a one-parameter family of quintics, and then you have also a group action. And this group action that acts by scaling an xi, which I won't tell you what it is, but maybe you've probably seen it, leaves x lambda invariant. And so therefore, it makes sense to consider quotient, call it y lambda, of x lambda by this group action. And so this y lambda I can call the singular mirror of a quintic. And let me say a little bit more about it. It's a toric projective hypersurface in which can be, okay, it's realized explicitly. So this is just using some toric techniques in mirror symmetry, I think due to Barteev, maybe Borisov. So it's explicitly defined as the projective closure in an affine in a torus. Let's call it g to the fourth. I think that's right. So this is like just c star to the fourth, or in the case that they will be considering for varieties over finite fields, it'll be fq star to the fourth, whatever. And it's realized as by the following equation: g of x1 to x4, x1 plus up to x4, plus 1 over the product of x1 up to x4, plus lambda equal to 0. The important part is that we have an explicit description as some function equaling to 0. It's rational, with rational terms. Okay. And so, yes. So we're still not done. I said that this is some singular variety or something like that. And so form a resolution of it. And this resolution I'm just going to call W lambda. Okay. And the family of these W lambdas we say are mirror to the family of quintic hypersurfaces. Okay. And so what do we have? So there's several ways of forming mirror pairs. On the one hand, you can take a generic quintic, x lambda, and pair it with one of these W lambdas. So you consider the family of these one-parameter hypersurfaces. You quotient by group action, you resolve the singularities, and you pick two guys from there. And I say that this is a mirror pair. And since I'm interested in talking about zeta functions, because this is just a generic element, I can, on the one hand, so for zeta functions, I can only say generic things about the zeta functions. So talk about generic properties in some sense. About the zeta functions of x, big lambda, and w lambda, okay, which is somehow unsatisfactory. And on the other hand, which is a little discouraging, these depend on a different number, different parameters. In particular, the w lambdas only have one parameters, but the x lambdas have many, 101. So the parameter spaces don't even agree. And so this creates this is somehow not exactly what we want. So to go around this problem, one has made a definition of a so-called strong mirror pair. Where you can take x lambda, so one of the quintic threefolds given by the polynomial I just erased, and w lambda, where they really are, I'm really taking the same parameter lambda for this mirror pair. Okay. And I say now here I can actually talk about the zeta functions of this and this variety, and I can see what can be said about them. So let me actually say what we should expect. So far, what happened? We said what a zeta function is. We have some way of defining a mirror pair. Maybe it's conjectural. Maybe, who knows, you're handed a mirror pair. And, or you're handed a pair of varieties, which you call mirror. And you can interpret them as making sense over a finite field. Okay. So this is why I can consider their zeta functions. Now, what kind of relation can you expect? Okay. So over C, complex numbers, consider m psi to be the just the family of parameterized by psi so what I mean here is that lambda equals -5 psi to the 5th, okay, for whatever reason. Now this is a one parameter subfamily of the 101 parameter family of quintics, okay, they're Calabi-Yau. And psi minus 50. Ah, yes. Okay. And so yesterday we saw a hint that the number of points on an element M inside this family can be thought of as some kind of p-adic period. So as a p-adic period integral. If you remember, we calculated a number of points using some character formulas, and I argued that if you write the series solution for the period of the quintic threefold, and you write the number of points, you get very similar expressions. Okay. So keep this in mind for a moment. Now, so periods have something to do with variation of complex structure. Maybe I should have just kept that. So okay. And so when I say variation of complex structure, I mean something like sending f of x0 through x4, depending on this parameter, to something like x psi minus 5 delta psi q plus delta cv x to the v, where q is x1, x0 through x4, so the product of the variables. It's just a monomial. So I'm adding some kind of parameterized monomials. And cv is a complex number. And x to the v is just notation for x0 to the v0 up to x4 to the v4. Okay, so this is also some kind of monomial. And so, in how many ways can I do this? Well, there are 126 monomials x to the v. Some kind of basic counting argument you can make. But I want to consider them modulo the ideal generated by the partial derivatives of f with respect to the variables. Okay? And in this case, this gives me 101 monomials. Okay? On the other hand, if you have q and you have a monomial, I claim that there's a way to associate a unique period integral to such a pair. You do something like you put the monomial in the numerator, and in the denominator you put w psi. Maybe you take some residues, you integrate, and the point is you get some kind of period integral from the data of monomial in q. And furthermore, since period integrals satisfy these differential equations, if you differentiate with respect to psi, thanks to the Griffiths-Dwork method, and I'm being vague on purpose, you are it corresponds to multiplying by q in the numerator. And so what does that mean in particular? Like, what am I trying to get at? Well, so how can I multiply by q? You can start with 1, multiply by q, get q squared, get q cubed, and then if I multiply by q again, I get q to the 4th, but you can verify that this isn't the ideal that I wrote over there of partial derivatives. And on the other hand, if you take a monomial times a monomial that isn't 1, and you multiply it by q, you end up with something like x to the v q. And now, okay, so there's what this means is that as I'm differentiating by psi, something that's determined just by 1, there's gonna be a linear relation among the higher derivatives that are determined by q, q squared, and q cubed, right? Because I said a monomial determines multiplying by q somehow corresponds to differentiation by psi, and right. And so this really means that there's some kind of linear relation among the derivatives. And here I get the same thing. And so here I have a degree 2 relation, so degree 2 degree equation, differential equation. And here I have degree 4 equation. Now there's only one of these guys, but as I go through all 101 v's, I get 101 differential equations. And so the combined solution space of these differential equations will be 2 times 101. So two solutions for each of these differential equations. And what I mean by that is each this data, this line and this line each determine some differential equation in a mysterious way, plus 4 solutions for this guy, and this is just B3 of M. Okay, and so this leads to since I said, okay, so these solutions correspond to periods, and periods somehow count points. Okay, so I said a p-adic version of the periods determines the number of points on the corresponding hypersurface. What this whole vague discussion leads to is that you can write the number of points with coefficients in fq to the k of f psi equals 0, so the quintic. You can decompose it as a sum of terms which correspond to these x to the v's and this q. So this is q and sum over all the v's and k x to the v in some way. So this is just some period expressions that correspond to this pair of data. Okay, and so what that means is that I expect somehow the zeta function, well, maybe it doesn't mean that, but it's a suggestion that the zeta function might somehow depend on the number of complex parameters of the family. Okay, quintic threefolds. And so in fact, what you can show, can show the zeta function of some threefold, generic, let's say, is going to be again a rational function, well, conjectures, and on top you're going to have a degree 2 times h 2 1 plus 2 polynomial, and this is going to depend on psi. So from psi to psi, it somehow has a dependence on it, this polynomial. And the bottom, you're going to get the degree 2h11 plus 2 polynomial. And so it seems because of this, just because, so naively, just because h11 appears in the on the bottom and h21 appears on the top, I hope that if I construct a mirror, I can have some maybe not the zeta function that we're dealing with, but maybe I want to conjecture that there's some kind of quantum zeta function which you associate to a manifold that satisfies the following relation. So let's say manifold is a quintic, or degree dimension 3. For 3-dimensional mirror pair MW. Okay, so you have some mirror pair, and because of this appearance of these Hodge numbers, which are exchanged, I want to say, well, maybe this is true, right? This seems to suggest that. But unfortunately, you can't do that quite as easily as you would want. So what happens, in fact, so on the first hand, there's this dependence on psi that somehow, if you want this to be true, shouldn't really be there, right? Because what is the variation? How do these parameters determine mirrors? Are they the same? Are they not the same? Somehow this is unsatisfying. But on the other hand, if this were true, if zeta just equaled zeta q, this quantum version that I want to satisfy that relation, was just the usual zeta function that I defined in the beginning of the talk, then this would imply, you can verify this maybe as an exercise, that the number of points on M equals minus the number of points on W. And so this is something we don't want. In fact, it's a contradiction. And so we have to keep looking. And let me tell you the direction in which this goes. So Candelas, De La Osa, and Rodriguez Villegas they showed that, well, first of all, for a mirror pair, M psi W psi, where here M psi is the quintic threefold and W psi is its mirror, you have the zeta function of the threefold of the following form. The product of three factors, R1, Ra, and Rb, divided by 1 minus t, 1 minus pt, and this is over fp, 1 minus p squared t, 1 minus p cubed t. Okay, so this is the m, and the zeta function of the mirror partner given by r over 1 minus t, 1 minus pt to the 101st power, 1 minus p squared t to the 101st power, 1 minus p cubed t. Okay. So first of all, this is interesting to begin with because like of the numbers that keep appearing 101 all over the place, and then these correspond to some kind of Riemann curves that weren't seen in the quintic before, and so on. But if I want a relation of this kind, well, it doesn't work as stated. But they looked at the large complex structure limit. Okay. And in this limit, what they wanted was to identify the denominator of that function with the large complex structure limit of R1. And they wanted to identify the denominator of this function with a large complex structure limit of the numerator of that function. Okay? And so what that amounts to, so want something like R1 of t psi going to infinity to be 1 minus t, 1 minus pt, 1 minus p squared t, 1 minus p cubed t. And at the same time, zeta of m infinity, whatever that means, is going to be 1 over zeta w infinity t, okay, which is just 1 minus pt. This is the requirement that they want. 1 minus p to the 101 and 1 minus p squared t to the 101. So maybe what these relations that we are seeking encompass is that this isn't true for just zeta functions, but maybe it is true for a large complex structure limit, because okay, these periods seem to have some that enumerate points seem to have something to do with variation of Hodge structure, and the mirror symmetry seems to be doing something kind of nice to the zeta functions. So since this large complex structure limit gives you a nicer correspondence of these parameters, scalar and complex, maybe that will work. And in fact, the same authors, showed that if 5 divides p minus 1, then we have the relation, the zeta function of m psi t congruent to 1 over psi w, 1 over zeta of the mirror is congruent to 1 minus p t to the 101 times 1 minus p squared t to the 101 modulo 5 squared. So in other words, we're working in, or let's say, C5. So there seems to be something about this, this hypothetical correspondence. Okay, so that motivates the kind of things that we're interested in. And with that, let me give you some results by one who's kind of, I think, examining this sort of mirror symmetry of zeta functions. This was meant to be a little just illustrational. It's not. So let's return to the mirror pair, strong mirror pair, x lambda, w lambda. Well, first, the number of points nk with coordinates in fq to the k is closely related to the reciprocal polars and zeros of the zeta function. So if the zeta function is equal to the product of 1 minus beta I t divided by the product of 1 minus gamma jt, okay, then just by manipulating the definition, you have that the sum of nk t to the k, or k equals 1 to infinity, equals the sum over j gamma jt over 1 minus gamma jt minus the sum over I beta it over 1 minus beta it. So in other words, these beta I and gamma j are just the alpha ij's from before that appear in the numerator and the denominator of the zeta function when written as a rational function. Okay, so they're closely related to the number of points. And okay, what does this mean in particular? Let me just so this thing will imply, if you look at it a little bit, that nk equals sum of gamma j to the k over j minus sum over I beta I to the k. Okay, so as I said, the number of points seem to be related to these reciprocal roots and poles of the zeta function. And furthermore, define for any alpha in CP, a p-adic number, the slope of alpha to be just the p-adic order of alpha with respect to p, or if you're working, yeah, or if you have varieties over FQ, then maybe the q-adic order. And with this definition in mind, it is possible to show from the Weyl conjectures that the slope of the reciprocal poles and zeros is between 0 and 2d, where d is the dimension of x lambda. And furthermore, that they are rational numbers. Okay. So there's that. So that brings us to, and now this whole, I just gave you this whole remark, that conclusion remark, but I gave you a remark, first of all, to define what slope means, okay, and to tell you something about it. So these are rational numbers. And second of all, just to give you an impression that the number of points is related to these reciprocal poles and zeros kind of closely, okay? And so that if I don't manage to convince you that this theorem is true, at least maybe you'll find it believable. So that brings me to the theorem. So suppose you have a pair of manifolds, which I call strong mirror, which two manifolds depend, with the same parameter in some way. So strong mirror pair of Calabi-Yau manifolds defined in the sense of yesterday over FQ. Then, on the one hand, for every positive integer k, we have that the number of points on x lambda with coefficients in FQ to the k is congruent to the number of points of y lambda with coefficients in FQ to the k, which is congruent to the number of points of w lambda with coefficients in FQ to the k modulo q to the k. And on the other hand, let me start somewhere else. On the other hand, this is equivalently, so this isn't an especially new statement if you believe that one. So if we define the slope zeta function of the 0, 1 part, written like this, to be, for any x, to be the product of the factors appearing in the full zeta function of x, 1 minus alpha I t to the appropriate power, plus or minus 1, such that alpha I is so one of the beta i's or gamma j's, and such that the slope of alpha I, so the q-adic order, is restricted between 0 and 1. Okay. Then the previous part will just imply that the slope 0, 1 part, zeta function of these x lambda t, y lambda t, and w lambda t, oops, 0, 1, are equal. Okay, so this congruence doesn't give you, so for the functions to be the same, you really need you can't have just congruence, you have to have equality. Okay, but we have congruence, and that is enough to give us that maybe not the whole zeta function of these varieties are the same, but certainly a part of them. Okay, and so before I talk about how this relates to the observations from before, let me just give you a quick illustration of the proof, a 2-minute illustration. So last time we used some kind of character formulas, right? We said that, and now there's a generalized version of character formulas. Which said something like the sum of t and fq. So, and maybe actually you're taking, yeah, okay, of t to the k equals either 0, q minus 1, or 1. So 0 if q minus 1 doesn't divide k, q minus 1 if q minus 1 divides k, but k is greater than 0, and 1 if k equals to 0. This is the same formula as yesterday, except I'm not summing over fq star. I'm just summing over. I'm summing over all of fq, and in fact, I yesterday summed over fp, but it's the same principle. And t from before might be Teichmuller of t, but this is essentially the formula. The point is, whatever appears in the exponent of the summed will have to satisfy some kind of congruence conditions, right? So you'll have to be divided by the q minus 1 or something like that to contribute to some a term to the counting of points, right? And so what you do is you essentially use this character formula along with Gauss sums that I mentioned, and the explicit description of x lambda and y lambda. So here y lambda, remember, had some kind of description as a sum of x1, x2, x3, x4, 1 over the product of all the variables plus lambda. And so, and if you remember, when you apply these the dwarfed character and Gauss sums, you end up with just a product of terms like this, depending on the monomials of your expression. You may be worried if you think about this in the future. You might be worried about this y to the lambda because it has negative powers of the coefficients, but it doesn't actually matter because the formula holds just as well. So you don't actually need to have a polynomial only. You can have a rational expression as well. The point is you just use all these ingredients and kind of automatically you just show that the expression for the number of points modulo some power is going to be this. You know what the expression for the number of points for these three guys are, and then you just reduce mod q to the k to get rid of some pesky terms, and you get this result. And then part 2 follows from it. Okay, so this is a proof of the theorem. Okay, but so somehow it seems like this slope stuff, the slope of these reciprocal porals and zeros is preserved by mere symmetry in some kind of way. And so for that reason, there's a conjecture that tries to capture in spirit what I was talking about, what we should expect, maybe. And the conjecture says that if we define the slope zeta function as, call it SP of a variety with respect to two variables now. So there's two variables, u and t, where you just replace in the zeta function all the alpha ij's with the variable u. So you get the product of terms like 1 minus u to the order q of alpha ij times t to the plus or minus 1 power. So if you do this, and based on what I said before, and on some further evidence that I don't have time to write, you have the conjecture that for some kind of strong mirror pair x and y, and maybe these are schemes of finite type of dimension d, and maybe they satisfy some other properties, maybe not. These slope zeta functions should somehow be related let's do this. So it seems that mere symmetry is nice to zeta functions and vice versa. And sorry if it was a little vague, but I'm just learning this stuff, so that's all I have to say.
Any questions or comments? Well, that one will be here next week, so you will hear more about this. It works.